In this video, I'm going to demonstrate how to graph a secant or a cosecant function in the Connect and ALEKS systems. So this specific problem will involve a secant function, but keep in mind you would graph a cosecant essentially the same way. So, as with all graphing problems, just a few words of advice before we get started. Number one, make sure you read the directions very carefully. In this case, there are specific directions about what the system wants in order to graph accurately, and you need to make sure all those features are there in order for the system to accurately generate your graph. Number two, as always, please make sure you do your graph on paper first. Identify all the attributes of the graph it by hand, and then translate your graph into the homework system. That typically results in best outcomes, and if you make a mistake graphing online, it'll be much easier to find it if you have your work written down on paper. So our function is y is equal to -6 times the secant of x over 4. And so to draw the graph, we want to plot 3 consecutive asymptotes and 2 points, one on each side of the second asymptote, so the asymptote in the middle. So we'll need 3 asymptotes in total and 2 points in total. So keep that in mind as we generate the graph. We need all of those features in order for it to graph accurately. So let me flip over and we will look at this on paper. Okay, now this problem didn't specifically ask to identify the features of the graph, the amplitude, the period, the phase shift, the vertical shift. It just asked for a graph. But I like to start by identifying those features anyway because they need to ultimately be reflected when we generate the graph. So remember, with our secant and our cosecant, those functions are typically defined in their relation to sine and cosine. Specifically, they are the reciprocals of sine and cosine. So as we graph this secant function, we're going to use the fact that secant is the reciprocal of the cosine function, and we're ultimately going to start by graphing the related cosine function, and then graphing the secant will be easy once we have that done. So in addition to graphing this function, we're also going to focus on graphing the associated cosine function. So essentially imagine the function that has all of the same features except it's a cosine instead of a secant. We'll think of this function's graph as the guideline for generating the graph that we actually want. So let's go through the graph features first. Number one for the secant, but also as well for the cosine, since we're kind of going to be graphing 2 and 1. Now, as far as amplitude is concerned, this is probably one of the most common mistakes when it comes to graphing a cosecant or a secant. Those functions actually do not have an amplitude. So amplitude represents how high and how low the function's graph can go. Well, secant and cosecant graphs actually increase and decrease without bound. They're not bounded above and below. So they don't actually have a maximum, therefore they don't actually have an amplitude. However, our cosine graph will have an amplitude, and so generating the cosine graph will require us acknowledging what its amplitude is. So the amplitude for the actual function we want, there is none. It doesn't apply. There is no amplitude for a secant function. However, our cosine function will always have an amplitude, and it's always going to be the absolute value of whatever the coefficient is on that cosine function. So in this case, it'll be the absolute value of -6, which is 6. So that tells us from the midline, we're going to go 6 units up, we're going to go 6 units down. It's also worth noting that negative in front of the 6 that disappeared when we took the absolute value. Remember, a negative in front of the function is going to reflect the graph vertically. So what normally would be graphed above the x-axis will be graphed below, and vice versa. So it's worth making a note of that. When we graph this, we will have a vertical reflection. So when we plot our points, we need to make sure we're reflecting them all vertically. Now let's find the period. Secant, cosine both have a period, and they're going to be the same. So standard period for cosine is 2 pi, therefore the standard period for secant is also 2 pi. And then we have to divide by whatever the coefficient is on x. Now, be careful here. It's x divided by 4, which would be the same thing as 1/4 times x. So the coefficient on x is actually 1/4. So 2 pi will actually be divided not by 4, but by 1/4. So to execute this fractional division, we change to multiplication by the reciprocal of the denominator. So our period is going to be 8 pi. So essentially 4 times as long as the standard cosine and secant periods of 2 pi. So essentially the graph is stretched horizontally. Now, phase shift. If we have any addition or subtraction inside of the trig function, that's where we would get a phase shift. We don't have any addition or subtraction, so there is no phase shift, so we won't have to worry about that. Vertical shift, that would be an addition or subtraction outside of the trig function. Again, no addition or subtraction, so no vertical shift. So the two things that need to be indicated here on our graph are the change in amplitude plus that vertical reflection, and then the change in period, which is going to take the graph and is going to stretch it horizontally. Okay, now for the time being, we're going to focus on just generating the cosine function, because again, that's going to be used as sort of a guideline for generating the secant function, the one whose graph we actually want. So let's start by generating the starting and end points for our standard period. Now, standard period for cosine and for secant goes from 0 to 2 pi, and so we want to see how this change inside the function affected those endpoints. So I'm going to write my inequality. So 0 is less than or equal to x over 4 is less than or equal to 2 pi. Okay, standard starting and ending points, we want to know how does that 4 affect that. So once we once we move the 4 and isolate the x, that's the word I'm looking for, we isolate the x, we'll know what the new starting and ending points are. So 4 is divided, I'm going to multiply it to move it over. Make sure you multiply both endpoints by that 4, so 0 times 4 is still 0. And then 2 pi times 4 is going to be 8 pi. So our starting and ending points are 0 and 8 pi. So notice the 0 stayed the same. The reason it stayed the same is because we didn't shift. If the 0 changed, that would be an indication that this graph has been shifted, either to the left or to the right. Since it hasn't been shifted, that starting point didn't change. What did change was the 2 pi. It became an 8 pi. So notice it's 4 times the size of 2 pi, and also that 8 pi corresponds to the period. So to go from 0 to 8 pi, it takes 8 pi units, hence a period of 8 pi. So when we graph and when we label our axes, we're going to label from 0 to 8 pi horizontally. Now we also need to know, as we travel along our period, graphing 4 equally sized intervals, where are those key points along those intervals going to fall? So if we take our period of 8 pi, divide it into 4 equally sized pieces, 4 equally sized intervals, which is the same thing as 2 pi, that is how far we're going to travel to go from one key feature on the graph to the next. And that applies not only to the secant, but also to the cosine. So all of these values fit with both the cosine and the secant. Cosine is going to give us basic points to start with, and then we'll graph the associated secant points based on that. Okay, so let's work on our labeling. Okay, so vertically, the only thing we need to label vertically involves our amplitude. Our amplitude changed from 1 up to 6 for our cosine. Now, we don't shift vertically, so that means, vertically speaking, the center of our graph is still at 0. But whereas we normally go up to 1 and -1, we're actually going up to +6 and then down to -6. So those will be our new relative maximum and minimum locations, 6 and -6. Okay, now let's look at the horizontal labeling. We need to start at 0, we need to end at 8 pi, and we travel between the two by going along increments of 2 pi units. So starting at 0, okay, and then our period is broken down into 1, 2, 3, 4 equally sized intervals, ending at 8 pi. And between our starting and ending locations, we're counting by 2 pi units each time. So 0 plus 2 pi takes me to 2 pi. 2 pi plus 2 pi takes me to 4 pi. 4 pi plus 2 pi takes me to 6 pi. And 6 pi plus 2 pi takes me to 8 pi, which is exactly where I want to be. Okay, now that everything is labeled, we can start to put some points on the graph. And again, we're not going to start with the secant, we're going to start with the cosine. So imagine for a moment that you're graphing a cosine. All the labeling is accurate for that cosine. We just want to put in the points for that associated cosine function. Now, keep in mind, there's no way to indicate this just with labeling, but that vertical reflection is something that we have to make sure is indicated on the graph. So cosine normally starts at its relative maximum, which would be at 6 in this case. If we reflect vertically, the graph is now going to start at its minimum, at -6. So that'll be our first point there at -6. Now, cosine then goes to its center line. It's going to do the same thing here. Okay, and then where our normal cosine hits its minimum, we reflect that vertically and it's going to hit the maximum. And then we just finish it out using standard cosine points. Okay. Now, 3 of these points are points that will actually be on the graph of the secant, and 2 of the points are points that will not. So remember, wherever cosine is 0, if you were to attempt to take its reciprocal, in other words, find the secant, you take the reciprocal of 0 and it's undefined. So what that looks like on a graph is anywhere where our cosine hits 0 or hits its midline, wherever that happens to be, those will be locations where the secant is undefined, or more specifically, the secant graph will have a vertical asymptote. So within that one period of cosine that we graphed, there's 2 locations where our cosine is going to hit its midline, and those are going to be the 2 locations where the secant is actually going to have a vertical asymptote. So I'm going to put in my vertical asymptotes at those 2 locations. Okay, and then the other 3 points are actually going to be shared points between the cosine and the secant graph. So anytime the cosine hits its relative maximum or its relative minimum, if you were to take the reciprocal of the cosine value at that location, you'll find that the secant has the same value. So those are going to be shared values. So essentially what you're going to have then is curves that emanate from those points and are bounded by the asymptotes. And that's going to be the standard secant graph that we draw. Okay, now everything's good on paper. Now we need to translate it to the homework system. Now, if you think back about what the directions said, the directions specifically said that we want 3 asymptotes and then 2 points, one on either side of that center, that second asymptote. In this case, we actually only have 2 asymptotes, so we don't quite have enough to get the accurate graph that Connect Math or ALEKS is going to want. But let's start by just putting what we have onto the grid, and we'll see what we need to do from there. So we have enough information to generate the whole graph. It's just not quite on our paper right now. So let's flip back over and let's see if we can input what we have so far. Okay. So we have a vertical asymptote at 2 pi, a vertical asymptote at 6 pi, and notice our grid is already marked, counting by increments of 2 pi. So we can just drag and drop those vertical asymptotes. So we've got one at 2 pi, and we've got one at 6 pi. And then if we want to put the points we already have, we can do that as well. So we had a point at 0, -6, so there's one of the points. We have a point at 4 pi, +6. And then we also had a point at 8 pi, -6. So there's our points so far. Okay, now again, we have 2 asymptotes and we need 3. And so what we need to figure out then is where our additional asymptotes would go. If we wanted to keep graphing, where would they go? Keep in mind, anytime we graph a single period, we're really just getting a snapshot of what the graph looks like. But the fact that our trig functions are periodic means they continue to the left, they continue to the right forever. So if you ever wanted more graph, more points, more asymptotes, all you need to do is continue generating and following that pattern out to the left or out to the right. Now, one thing to notice here on the grid that we have so far is once we hit that point at 8 pi, we essentially fall off the graph. But we do have graph to the left of the y-axis. So more than likely, if we want to add some additional stuff to this graph, it's going to have to be something that's to the left of that point at 0, -6. So notice out to the left of that 0, -6, we have another tick mark labeled at -2 pi. So let's see if we can actually use that. So let me flip back over to the paper and we'll see what we need to do. Okay, so we started our standard period at 0, went from 0 to 8 pi. If we need an additional asymptote, we follow that same pattern based on how we travel from one key feature on the graph to the next, namely that we always travel by 2 pi units. So we traveled by 2 pi units in the positive direction. You could do the same thing in the negative direction. So for example, if I traveled 2 pi units out to the left, which would take us from 0 to -2 pi, I would land on another location where I have a key feature. So notice at 0 we had a point, at 2 pi we had an asymptote. 4 pi we had a point, 6 pi we had an asymptote. So if we follow that pattern in the other direction, negative 2 pi will also be a location where we have an asymptote. So every time we hit negative 2 pi, 2 pi, 6 pi, next asymptote would have to fall at 10 pi. Those are going to be locations of asymptotes. And then the points are going to fall halfway between each of those asymptotes. So if instead of graphing that interval from 0 to 8 pi, if we shifted it a little bit and graphed the interval from negative 2 pi to 6 pi, notice we have 3 asymptotes, and we have 1 point to the left of the center asymptote and 1 point to the right, and that's exactly what our system was looking for. So let's add in that other asymptote, and we should have everything we need. So we have a new asymptote at negative 2 pi. Okay. Now our center asymptote is at 2 pi. Let's double check that we have everything. We need 2 points, one on each side of that second asymptote. So we have that point at 0, negative 6, that's to the left. We have the point at 4 pi, positive 6, that's to the right. So we have everything we need. We'll click the graph a function button, and notice it graphs the function exactly as we expect. So let's check the answer. And it looks like we're good. Okay. So as usual, what happens, what does it mean if for some reason you graph that function and the shape is not right? More than likely it means either you're missing information, you didn't graph as many asymptotes or as many points as you needed, or it means one of those items is wrong. So if you misplace an asymptote in the wrong location, if you put a point in the wrong location, the system's not going to be able to generate an accurate graph. So go back to your paper, double check everything you did on paper first, make sure you translated that over accurately, and if there is a mistake in the paper, make sure you can identify that, and that's going to help you fix your graph. So that's going to be graphing secant and cosecant functions in the Connect Math and ALEKS systems.